goal for today is to get through the quote-unquote easier synthesis problems, and then we'll work on the harder ones tomorrow. So for this, you have these slides. I went through and I just printed out the slides, but what I did is I left blanks so we can fill it in and you can kind of add to this as well. So essentially what we're doing with these synthesis problems is we're taking a reactant and we're kind of retracing our steps to figure out how can we get to a certain product. So instead of just showing the mechanism, right, or just showing the product of a single reaction, this is looking at going through 2 or 3 different steps to take a reactant and go to a product. And so as we go through, for these synthesis problems, again, this is taking, nothing. There it is. Okay, there we go. So this is taking a reactant and turning it into a product. But for these synthesis problems, these are multi-step reactions. So this looks like a single step, when in reality, we would need multiple steps to take this starting terminal alkyne and ending with an alcohol. And so what we're going to do is we're going to look at how would we know all of these steps to take this terminal alkyne and end with this alcohol. So we're going to look at the different things that we would need to look at. Now, just to kind of go through and explain what this does, right? So we'll kind of add this in onto this slide. We have everything, right? Step 1, 2, and 3. And sometimes some of these steps go together. This is going to become one that we're going to see often. Na and NH3 or H2 and Lindlar's catalyst. And so Na and NH3 or H2 and Lindlar's catalyst, this is hydrogenation. Now you don't need to know the mechanism for hydrogenation, but the reason that we put this or is because Na and NH3 produces a trans alkene, H2 and Lindlar's catalyst produces a cis alkene. So if we need that stereochemistry in a certain way, we might need to use one over the other. I will always put the or. Most people would probably use this, only because when you draw your product, if you use the zigzag, or you use just the zigzag structure, it's going to automatically put it in trans. So a lot of people will probably use that Na and NH3. So again, what I'm going to do is I'm going to show each of these just so we have another example. So here we have a terminal alkyne. Now that might be useful, so I like labeling when it's terminal. Remember, for hydrogenation, we don't need the mechanism. So I'm just going to put no mechanism. So if you're looking back at this, you're like, why didn't I draw the mechanism out? You don't need the mechanism for any hydrogenation reactions. You don't need to know how they work. You just need to know what your products are. And so for hydrogenation, when you have Na and NH3, or you have one H2 and Lindlar's catalyst, you produce an alkene. So you are not changing the number of carbons. 1, 2, 3, 4, 5, 6 carbons in the starting reactant. You should have 6 carbons in your alkene. So if I draw this, 1, 2, 3, 4, 5, 6. All hydrogenation does is it produces an alkene with either of these as reagents. If you have excess H2, that's going to take your alkyne and go directly to an alkane. But when you have one of these 2 sets of reagents, it's going to go to an alkene. So step 1 creates this alkene. Then we have BH3 and NaOH and H2O. Now these actually go together. If you look at your reference sheet or you look at your notes, boron, we looked at hydroboration. And so this is actually hydroboration oxidation. So what we're doing right now, I gave you these steps. We're actually taking it through step by step to see how we take that reactant and we go to this product. So steps 2 and 3 go together. And so on your reference sheet, it would probably look like this, except it'd be a 1 and a 2 instead. For us, it's step 2 and 3. We already went through step 1 of hydrogenation. Hydroboration oxidation, you also don't need to know the mechanism for. You just need to know the products. So we take that BH3 and OH minus and H2O, and that allows us to add an alcohol. Now notice how we had an alkene and it ended as an alkane. This is one of the alkene reactions that we looked at. If we look at this again, a key thing that I notice here is that the OH added anti-Markovnikov. So as we start to look at these synthesis problems, we're going to look at some of these considerations. How did something add? Are we ending with an alkane or an alkene? So what reactions might they need to have gone through to get from an alkene to an alkane or an alkyne to an alkene, so on. And so that's what we're looking at as we go through, these different steps. So this is just giving an example of if these were 3 steps, right, we can have multiple ways to get from a reactant to a product. And then this just kind of shows the same thing. So kind of some tips for solving. So as we're solving these synthesis problems, things that you always want to do, start by counting your carbons. Okay, start by counting your carbons and look and see, did your chain get longer? Did it get shorter? Right, in the do now, we looked at the 2 types of reactions that allows us to lengthen a carbon chain or that allows us to shorten a carbon chain. So if the chain got longer, we have to go through chain elongation. If it got shorter, it would have to undergo a cleavage reaction. So then we can look at our reference sheet, right? What forms what? Are there specific functional groups we're looking at? Specific things we're ending with, and then we can kind of work backwards. This is a lot of problem solving. This is not just, okay, here are the reactants, here's the product. You have to kind of think about how do you go from step A to step B to step C. So just kind of some patterns. There we go. All right, just some patterns, right? Some examples to look at. If you're making an alkane, right, all single bonds, usually you start with an alkene. So if you're ending with all single bonds, you're probably going to start with a double bond. There's only one way you get an alkane from an alkyne, and that is complete hydrogenation. That's a single step, though. If you want to add carbons to a chain, you need a terminal alkyne. Now, something to keep in mind as we go through this, if you need to add carbons to a chain, we said that that's chain elongation. Elongation must always happen first. So chain elongation must always occur first. Because with chain elongation, all you're doing is adding carbons to the carbon chain. That triple bond stays intact. So if you want to add carbons, you're like, okay, I'm starting with 5 carbons, I need 6. That's chain elongation. You always do that first. And then you look at what other reactions could take place to get from that alkyne to something else. So for the chain to get longer, that's chain elongation. For the chain to get shorter, those are cleavage reactions. Both alkenes and alkynes can undergo cleavage reactions. It's just what you want the product to be. And so we'll take a look at kind of these, quote, easier synthesis problems. These show us the number of steps. So for this first example, this is showing us that we have 2 steps, right? Step 1 gets us this intermediate. Step 2 gets us this product. Now, before you worry about the reactants, right, what we form, always start by going through those steps. Start by counting your carbons. So here we have 1, 2, 3 carbons. So there's 3 carbons in this starting chain. Here we have 1, 2, 3, 4, 5 carbons. So number of carbons has changed. So down here, I'm just going to say added 2 carbons to the chain. If you are adding carbons to that carbon chain elongation must happen first. All right, so this means that it's undergoing chain elongation. Now we come back here, so we know this is going to be chain elongation. You're adding carbons to that parent chain. So then we can look back at our reference sheet, or we can look at our alkyne notes, because this is a triple bond. Elongation can only occur when we have a terminal alkyne. You must have a terminal alkyne for chain elongation to work. And so if you look at your notes, or you look at your reference sheet, one of the reactants is NaNH2 and NH3. And then the second reactant is based on how many carbons we need to add. If we need to add 2 carbons, that means this Rx group, right? So we always have this Rx. R is the number of carbons, X is a halogen. Typically we see X as Br. This R group is based on how many carbons need to be added. So if 2 carbons need to be added, we have Br at the end. So we would say this is CH3, CH2. Now I always have people say, can I just draw it instead? So can I just draw it as, here's a C connected to Br? Sure. And that's the same thing. But what this second reactant is this is based on how many carbons you want to add to that parent chain. So for chain elongation, I'll show you the mechanism, just to kind of review the mechanism for this, how it works the way that it does, just to show you how to get to this product. So if we take a look at this, right, the mechanism for chain elongation, we need this NaNH2 only because NH2 is a strong base. So what happens is that NH2 is a strong base, that Na is just a spectator, but off of this terminal alkyne, there's a hydrogen. During chain elongation, this lone pair on the strong base is going to take the hydrogen. When the NH2 minus takes the hydrogen, these electrons in the bond go directly to that carbon. This creates a carb anion. And so 1, 2, 3, 1, 2, 3 produces this carb anion. And then we have NH3, right? That's why we have this NH3 here. That's the solvent that it's in. But then with this carb anions are extremely reactive. And so what's going to happen with this carb anion now, here is the CH3CH2Br. So you could redraw this CH3CH2Br with the bond line structure. This lone pair is going to attack the carbon bonded to the bromine, bonded to whatever halogen. Halogens are very good leaving groups. What that means is when these lone pairs attack this carbon, these electrons in the lone pair will go to bromine. We have Br minus floating around in solution. That's okay. Halogens are okay with having that negative formal charge. And then what happens is now this carbon has bonded to this carbon, and we've added 2 carbons to this chain. So what this looks like, we have 1, 2, 3. So here's this. Now this carbon is bonded to 1, 2 more carbons. And so if we draw this, 1, 2, 3, 4, 5. And if it helps you to just put dots where the carbons are, there's your 5 carbons. So chain elongation always has to happen first. You don't have to show these mechanisms as you go through these synthesis problems. I just went through the mechanism just to show you how it works, just to review the mechanism for chain elongation. But every time you go through these synthesis problems, you don't have to show the mechanisms. So here was chain elongation. So now we have an alkyne. We're ending with an alkene. So now other things you want to think about is how can we take an alkyne and go to an alkene? Now based on this alkene, I'm going to just label this a little bit more. Your 2 alkyl groups. So here's CH2, CH3, and here's just CH3. They're on opposite sides of the double bond. So what kind of alkene is this if they're on opposite sides of the double bond? Trans. And so this is producing a trans alkene. So if you're taking an alkyne, right, you know you're starting with an alkyne, so it's going to be one of your alkyne reactions, and you are ending with a trans alkene. When you want to, I say remove, and we're not actually removing it, but when you want to eliminate one of your pi bonds, that's hydrogenation. So you want to eliminate one of your pi bonds, you're looking at hydrogenation. Now you don't need to know the mechanism for any hydrogenation reactions. But now that we know that it's an alkyne going to a trans alkene, there's only one set of reactants that produces a trans alkene. And that's Na and NH3. Now I have some people that will look at this and they're like, well, if I draw this product though, it's going to look like 1, 2, 3, 4, 5. The double bond is between carbon 2 and 3, right? 1, 2, and 3. That doesn't look like this. If you were to rotate it, it would. All right, you can draw it differently. As long as you have 5 carbons, I could count from this way, 1, 2, 3, 4, 5, and the double bond is between carbon 2 and 3. We see hydrogenation occurring a lot with alkynes. So when you want to take a triple bond and reduce it down to a double bond, that's more than likely some sort of hydrogenation question. So again, you're not going to need to show the mechanisms down here. I just wanted to remind you like what elongation looks like, why it adds like it does. Questions on this one before we look at the next one? Yeah, but I don't think it's going to be Friday. Because I want to have time to review. So, yeah. All right, so let's look at this next one. Again, this synthesis is showing us the number of steps. Start by looking at your reactant and looking at your product. Count your carbons first. The first thing you should always do is count your carbons. If you have the same number of carbons, you don't have to worry about chain elongation. If you have different number of carbons, then you either need to look at elongation or cleavage. So if we look at our starting, again, I'm just going to label this a terminal alkyne, right? This is a terminal alkyne. The triple bond is at the end. There's 1, 2, 3, 4, 5 carbons in the starting alkyne. We are ending with 1, 2, 3, 4 carbons. So we're starting with 5, we're ending with 4. If you need to reduce your number of carbons, it's going to have to undergo some sort of cleavage reaction. Now, cleavage doesn't have to happen first. Elongation has to happen first because that only deals with triple bonds. Cleavage doesn't have to. The type of cleavage reaction that this is going to undergo is based on the product that's formed. Here you have H off to the side. What kind of functional group is it if you have C double bonded to O with H to the side?
Aldehyde.
Aldehyde. So this is an aldehyde that's produced. So if you take a look at your cleavage reactions, you have cleavage reactions for alkenes and alkynes. So the cleavage of alkynes, which we've talked about more recently, we have ozonolysis and we have permanganate oxidation. Both of the cleavage of alkynes produce carboxylic acids. So up here, I'll just make this note. Both cleavage reactions of alkynes produce carboxylic acids. So if you are cleaving a triple bond, you're cutting that triple bond in half, you produce carboxylic acids for both type of cleavage reactions. Now, if we look back at our alkene cleavage reactions, our alkene cleavage reactions are also ozonolysis and permanganate oxidation. The names are the same for both. But what we produce when we cleave an alkene bond, a double bond, is a mixture of either aldehydes and ketones or carboxylic acids and ketones. So I'll say cleavage. So this is just kind of reviewing these cleavage reactions of alkenes. I don't know why I put a comma there. Produce either ketone / aldehyde or ketone / carboxylic acid. So the cleavage reactions of alkenes will produce something different from the cleavage reactions of alkynes. There's only one that will produce an aldehyde. Now, this is only showing one of the products. There's going to be another one, but they don't have to show us both. But we know that this is an aldehyde, which means this was cleavage of an alkene. So sometimes before you can even figure out any of the reactants, you really have to kind of go through and look at what are you starting with, what are you ending with, and really what do we have to start with to get this product, kind of that in between. And so to create an aldehyde, you have to cleave an alkene. And so that means that this in between is going to need to be an alkene. So we have an alkyne, we're going to need to get to an alkene, and then we can actually undergo that cleavage. Now, we can kind of work backwards here because there's only one type of reaction that produces an aldehyde. And so if you look at your alkene cleavage reactions, the one that produces an aldehyde is ozonolysis. So ozonolysis produces that aldehyde. You don't need to know the mechanism. All right, no mechanism. I'm just kind of reviewing what you should know the mechanisms for and what you don't have to know the mechanisms for. So ozonolysis uses ozone, which is O3, and uses water and zinc. Again, you don't have to know the mechanism. All you have to know is that that will cut that double bond essentially in half and add oxygen to both of those double bonds. So now we have to get from an alkyne to an alkene. We'll worry about cutting it once we get to that alkene. This is where I said that hydrogenation becomes a very common step. If we want to get from an alkyne to an alkene, it will undergo hydrogenation. Now, you could have one of two sets of reactants. I typically will use Na and NH3 just because then when I draw my bond line structure, I can do the zigzag method. But just a reminder, this produces a trans alkene. Or, I'm going to put or here. You could use H2 and Lindlar's catalyst. That produces a cis alkene. Whichever one you pick is fine, but obviously make sure if you're picking the cis that you're showing it in a cis stereochemistry. Again, you don't need to know the mechanism for hydrogenation, but what we get when this undergoes hydrogenation is you are essentially eliminating one of the pi bonds. You're adding hydrogen to both sides. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And between carbon 4 and carbon 5 is that double bond. So we took an alkyne, went to an alkene, and then what happens in these cleavage reactions is you can kind of imagine this squiggly line here, and you put an O to both of those. Because this is a hydrogen, that's how we create the aldehyde. All right, then this is just C double bonded to O with H on both sides. We don't see this product over here. All we see is this main product. But drawing this squiggly line and then an O here, that just kind of helps you to see what that cleavage reaction looks like. So you have to just take that starting, right, your starting reactant, kind of look at that product and see what you would form. So, and this, on these slides too, it kind of goes through every single step that we wrote up here. But just see if, on the next slide, see if you can at least kind of just write down what you notice about the starting reactant and the product. So count your carbons, right, what you notice about both, and then we'll kind of talk through this.
Wait a second. How many carbons are there?
And if you notice, like for example, you have this cyclohexane, just kind of focus on what's coming off of the cyclohexane.
So that means that we're eliminating this.
So you notice you have the ring in both. You're going to have this cyclohexane ring no matter what. You're not really affecting that cyclohexane ring at all. But I heard some people saying that you're starting with an alkyne and ending with an alkane and adding that Br. So I heard people saying you have an alkyne, we're going to an alkane and adding Br, so we're probably going to have to go to an alkene. So you're figuring out a way to go from an alkyne, right, probably to an alkene. Here's where, again, we use hydrogenation often. I like using Na and NH3, produces the trans alkene. So I can draw, and this doesn't really matter because you have two hydrogens off of one side. But again, this is hydrogenation. You don't have to worry about the mechanism for it. Once you have an alkene, then you're looking at how do you go from an alkene to an alkane with that Br. Now you're going to notice over here, right, Br is adding anti-Markovnikov here. Most alkene reactions, you create the most stable carbocation, which would be here. Right? Bromine is not adding here. Bromine is adding anti-Markovnikov. It's adding to the less substituted side. So how can you add one bromine to the less substituted side? If you look at your alkene reactions, free radical bromination.
I don't like free radical bromination.
Now, we looked at the mechanism. Just to save time, I'll just go with the reactants and the products, but this is where you have one electron from the double bond combining with the one electron from the radical bromine. It adds anti-Markovnikov. And then you have the single electron on the carbon, adds to another HBr. For free radical bromination, you have HBr, and then you have peroxide. All right, you could also add light with the peroxide.
Can we just write peroxide?
Yeah, if you want to just write peroxide, that's fine. Yep.
Okay.
So you have HBr, peroxide, and what that does is that adds a bromine anti-Markovnikov, which is this, and it gets rid of that double bond. So it's a lot of like going through,
You have to know your stuff.
problem solving, using
like
your
this.
notes, using your reference sheet.
Exactly.
So for what I want you to try for tonight, the very last page of this says synthesis problems practice. So part A up here, I gave you a lot of like the reactants, maybe the reagents. I just want you to try part A, which is 1, 2, and 3 at the top. So a lot of this is actually just reviewing like the reactants, what's the product. You don't have to show mechanisms, but you're just filling in any of the key steps. And then we'll go over part A tomorrow. We'll continue looking at these synthesis reactions and continue to do more practice with it.